Hello everyone. In this video we are going to go over the companion slides and notebook prepared for week 7 covering the topics KNN and decision trees. First let us have a look at KNN. So first we have a look at the dataset. The dataset consists of 8 points with 4 of them belonging to class +1 indicated by the blue points and 4 of them belonging to class -1 indicated by the green points. So the points in class +1 are x1, x2, x3 and x4, whereas the ones in class -1 are x5, x6, x7 and x8. So now the way we do it in KNN is, first we take our test point, that is the one to which we want to assign a label. In this case we are taking a test point 2, 2, and depending on the value of k, we are going to find k nearest neighbors to this particular point, and of those points the label corresponding to the majority of the points is what will be assigned to our test point. So first we have a look at the distance of our test point xt with this point x1. So the distance of this is the Euclidean distance that we have calculated, and it turns out to be 1. Likewise, we are going to calculate the distance of the test point with all of the points in our training data set. So these values are indicated in this table here. So now that we have the distance of our test point with all other points, depending on the value of k, we are going to assign a label to this point. So first we consider the case of k equal to 3. So we need to find the 3 closest points to the test point and then assign a label corresponding to the majority. So for the point xt, we can actually see that there are 4 points x1, x2, x3 and x4 that are at a distance of 1 unit from xt. So of these 4, we can take any 3 of them to be the closest points, and the label corresponding to the majority will be assigned. So here we have taken x1, x2 and x3, and the label of these 3 points happens to be +1, which is why the test point will take a label of +1. Now if we consider the case of k equal to 6. So for k equal to 6, we take the 6 nearest points to our test point. We have 4 of them as shown here, +1, and x5 and x8, which are also indicated in the graph. And again the majority label of these points turns out to be again +1, which is why our test point will once again be assigned a label of +1. However, if we consider the case of k equal to 8, all the points in the data set end up being its nearest neighbors, and if we were to assign the label corresponding to the majority, we see that 4 points have a label of +1 and 4 points have a label of -1. So here we cannot definitely assign a label to the test point. Now let us consider another test point 4, 2, and again as we have done so far, for different values of k, let us try to assign a label. So we have a table containing the distance of the test point with all other points, and now depending on the value of k, we are going to assign a label. First we take a case of say k equal to 1. So here the nearest point that we take can be any of x4, x5, x7 and x8. So for the sake of this example, we will take it to be x4, and if you see, it has a label of +1. And now if I were to assign the same label to our test point, the test point would also take a value of +1. Likewise, now if I increase the value of k to be 5, we take the 5 closest points, and here if we have a look at it, the majority points have a label of -1, which is why the label assigned to our test point will also end up being -1. So changing the value of k is impacting the label that is taken up by our test point. So this value of k is something that is going to be important in this classification algorithm, and this value of k is in practice is k is a hyperparameter, and one way to identify a good value of k is through cross validation. Now we are going to have a look at decision trees. First let us go over the notations. We have D, which is the data set at the parent node. XF lesser than S is the question that we are going to ask to make a split, and then we have DL and DR, which is the data set in node L and R that we obtain after the points answer the question that we have here. And then we have the proportions at P, L and R, which is the proportion of points belonging to class 1. And then we have gamma, which is the proportion of points that have gone to the left node. And then we have 3 values of entropy for the 3 nodes, and finally the information gain. The formula for entropy is shown here, the formula for information gain is shown here. NP happens to be all the points in the data in the parent node, NL happens to be the number of points that have gone to left node, and NR happens to be the points that have gone to the right node. Now let us take an example to understand this better. So here we have 8 points, 4 of them belonging to class 1 indicated by green color, and 4 of them belonging to class 0 indicated by red color. Now we want to find the question which will lead to maximum information gain, and depending on that we can grow the tree. So the question will be of the form xf lesser than s, and if the answer to it is yes, it goes to the left node. If the answer to it is no, it goes to the right node. And now here let us understand this table. So here what we have is information gain for 1 comma s. Here 1 is the feature. So this will be 1 or x1, the feature x1, and we find the information gain for different values of s. The value for s can be 1.5, 2.5, 3.5, that is 1.5, 2.5, 3.5, 5 and so on, and the information gain for all of them is listed in this table here. Likewise, for the second feature, which is along this direction, we once again find the information gain for different values, that is 1.5, 2.5 and so on, and we have listed it down here. As you can see, the maximum information gain is seen when the value is taken to be 5 and the feature is the first one. So having done this, we see a perfect split between the points belonging to class 1 and the points belonging to class 0. Now let us take another example where we go through the entire process. So the first question that we ask is x2 lesser than 5.5, and as you can see, this is going to be x2 along this direction, and we ask if x2 is lesser than 5.5. So the points that will say yes to it are the points that are in this area, that are within this area. So those that have answered yes, that is these points here, will come to the left child, and those that answer no will go to the right child. And as you can see, DL has 6 green points and 9 red points. Likewise, on this side, the ones that have answered no will have 8 green points and 5 red points. The proportion of points, again if we see, the parent node is the one that is the entire data set. So in the entire data set, we had 8 plus 6, 14 points, green points, that is points belonging to class 1 among 28 total points. So the proportion is 14 by 28, that is 0.5. And the left child, that is the one that is in this area, has 6 green points out of 15 total here, which is why the proportion is 0.4. Likewise, for this side there are 8 points among 13 total, for which the value is 0.615. Now the entropy is given by this formula, minus p log p minus 1 minus p log 1 minus p. So if we take it for the parent node, we have the value to be 0.5. On substitution, we find the entropy to be 1. Likewise, we use the same formula for the left node and the right node with the values PL and PR respectively, and we find that the entropy value is 0.97 and 0.961. Now that we have this, we can calculate information gain. So information gain has entropy of parent, which is 1, and gamma, which is the number of points that have gone to the left child. So that, if you can see, is 9 plus 6, 15 out of 28. So the gamma value turns out to be 0.535. And then the entropy of left node is 0.970 and 0.961 as written here. And on calculation, the information gain ends up being 0.034. Now let us divide this part further. We are going to ask another question, is x1 lesser than 5.5, and those that answer yes are now assigned a label 0, and those that answer no are assigned a label 1. So assignment of the label is happening because here we can see that we now have a pure node. There are only points belonging to class 0 on one side and points belonging to class 1 on the other side. That is, they are going to have a very low value of entropy, which is why we can end up assigning labels to them. So the left child has 9 red points and 0 green points, and the right child in this case has 6 green points and 0 red points. Now the proportion of the parent node, as we see, is 6 green points out of 15, so 0.4, and 0 here and 1 here. The entropy, again, if we calculate, is 0.97 as we have seen previously, and for the left child, again, if we substitute this value, we are going to get 0 entropy, and likewise for the right child also we are going to get 0 entropy, and this time the information gain is going to end up becoming 0.97. Now we go to the other side, the section when x2, for the points that are for x2 greater than 5.5, that is this side, and we are again going to ask another question, is x1 lesser than 5.5. So once again we see that the points that answer yes this time are green points on this side and there are red points on this side. Once again, since we have pure nodes, the entropy is going to be 0, which is why we can also assign the labels to it. So the data set has 8 points on the left side that are green and 0 red points, and 0 green points here and 5 red points here. The proportion of points again is 8 by 13 is going to give us 0.615, and here there are, all of them are green points, so the proportion is 1 and here it is 0. Substituting these, again we get the values of entropy to be as shown here, and the information gain is 0.96. We are now going to look at both KNN and decision tree through the form of code. First we import the necessary libraries, and then we generate the data set, and on visualization we see that there are two classes. So one indicated by green and another by red. There is also a small portion of red points within these green points. Then we come to predicting the class for a test point. So to predict the class for a test point, first we need to find its distance with all the other points in the training data set. Once we have found that, we find the nearest k points to it, and depending on the majority of those k points, we assign a label. So for the test point that we had taken -3, -2, the label happens to be green. For different values of k, we are going to end up getting different decision boundaries. So for k 1, 3, 7 and 15, as you can see, the small portion of red points that were present are still playing a role, which is why we have the small red area. However, as we increase the number to 31 and 63, there are the majority of points end up being green, which is why the decision boundary is as shown. The same code that we have used for the synthetic dataset, we are now going to try it on a real world dataset called the wine dataset, where we have again taken a subset with two features, prolin and u, for two classes 0 and 1. First we import the dataset and have it as a numpy array, and then after scaling, this is how the points will look like. So we have a portion of green points and red points. Again, if we were to use the same function predict for a point -2, 0, the value given is green. We can try it out for different points with different number of neighbors, and we can see the class accordingly. For this particular data set, if we were to visualize the decision boundary when taking different values of k, this is how it changes. Next, we are going to have a look at decision trees. This is the example considered here is the same one that we have seen in the slides. We again have 28 points here, and on visualizing it is as seen with 14 green and 14 red points. We have the function for entropy and information gain based on the formula that we have seen in the lectures, and then we come to the function called best split. This function is the one that is used to identify the question that we need to ask. So it returns us the best feature, the value corresponding to it, as well as the information gain. We are going to use this in building our tree. So this function called grow tree is what we use to build the tree. So at the end of this function, what we end up getting is we will get 7 nodes that we see here, and with 3 of them being internal nodes, the corresponding question that is asked there and the values. Along with it, we also have 4 leaf nodes and the labels assigned to them. All these are stored in the dictionary object called tree. So the way this was done is by making use of the function best split and assigning it to be a leaf node depending on the entropy value, and the label was assigned based on the majority of points in that particular node. Now if we were to predict a label for a test point, we already have our tree object. We just need to pass this test point through that tree object, and depending on how the point answers to the various questions that we have in our internal nodes, it is going to end up in one of the leaf nodes, and the label corresponding to that leaf node is going to be assigned. So when we visualize the decision boundary for this particular example, we see it to be as shown, which is same as the one that we have seen in the slides. Thank you.